Ok. 55 é bom, não é? 55 minutos?
35?
55.
55, sim.
Okay. Okay, welcome back again. We'll now have a talk by Mr. Francisco Campuzano on ocean modeling with MOHIT for operations. Francisco Campuzano is an oceanographer and numerical modeler at Plus Atlantic Collab. He was formed in the University of Las Palmas de Gran Canaria in Spain and holds a PhD in environmental engineering from Instituto Superior Técnico and an MSc in Estuarine and Coastal Management and Science from the University of Hull. He was involved in more than 20 European and national research projects. He is co-chairing the ICSW GOOF working group and a member of 3 EuroGOOS working groups, IBRUS, Mongoose, and Coastal. He is a member of Copernicus Marine Service Champion User Advisory Group and member of several UN Ocean Decade Actions, and also steering committee member in Coast Predict and Ocean Prediction, DCC. He leads the EMODNet Physics River Node for providing near real-time river data. In recent times, he was involved in the development of oceanographic operational systems linking watersheds, estuaries, and the open ocean. He has led several European projects of operational oceanography and environmental management, and is the co-author of 22 scientific papers and 16 book chapters. Thank you very much.
Thank you very much. Thank you very much for reading this. Well, good morning, everyone. Thank you very much. I will start with a big surprise for all of you. This is the presentation with no Julia line at all. Okay, so this will be a big difference from the rest of the presentation. So I see myself as a potential customer or user. I don't know if user, more customer probably. I'm representing some of the oceanographic community and the ocean community that is using some of the products. So what I've been doing my personal brainstorm during these last couple of days to see how I can use some of the things that are being discussed here that I'm very impressed, and I will be, in 1 year time, showing a presentation with sun lines of Julia. This is the challenge. So I will do an introduction about our group, a little bit of our group, and what we do, and what are the things that I believe that we could use Julia for. And also have a challenge for you at the end, to see if I can come back home with something that then I can put hands on, or try to put. I have also a couple of colleagues here, so I can ask them to put their hands on. So my name is Francisco Campuzano, as maybe, I don't know if you get the name with this long presentation, and I work in Collab Plus Atlantic, that is an institution based in Portugal, and it has a very strong relationship with the AirCentre, and we are like our role is we are a non-for-profit association, so we have like 13 members. We have industry, we have also academy, and we have also national labs, and we are kind in between research and market. So the idea is to try to be something that develop further what are found in the universities, but we have these links to try to put all these groups together. Then we are new compared with many other institutions. We are like 5 years old, and now we have defined what are our main lines of activities and work. Some of them will be like supporting, all related with blue economy. I will tell you a little bit more about blue economy afterwards, but related with aquaculture and fisheries, we have applications with artificial intelligence too. We are moving also in meteorological and ocean forecast, and what is called now the digital twins. So we are working in this sense. And also we are providing some consultancy for the blue economy and try to build some tailor-made products. We have experts in artificial intelligence, numerical modeling, Earth observation. So many of the things that you were showing are very relevant to us. And we are a group of around 25 people. My colleagues, they say hello, they are colleagues of mine, so please also talk to them and try to involve them in the Julia thing. So why we do all our activities are mainly related with the blue economy and the coastal risk and management. So blue economy, for those of you that are not that used to the term, is a new name for something that is not that new. So like the economy is related to the ocean, so fisheries, aquaculture, ports, transport. I mean, there are some new things like marine renewable energy, deep sea mining. These are maybe new things, but most of them they were grouped in this sense, and they are like they need of information in the ocean to take the decision and to make some management, and they want information as accurate as possible, so then they can have a safer risk, safer coast from risk, like from floodings or apps or other kind of threats that we have. So basically, to do these forecasting systems, we need a lot of information. We use every single data that we can, and it's a lot of data. We use satellite data, even to find where are the fishing boats, to know the temperature, to know what we can observe. That also the satellites are limited to the surface, but then because of that we have also some floating buoys, gliders, many technologies. So this forecasting services is something that needs a lot of knowledge from many fields. So you need to know meteorology, oceanography, engineering, technological development, sensors, IT, data science, artificial intelligence. So this is a problem, in fact. We need to know and to talk to the different people with the different language and to use this. So the idea is that we put all this information and all this observation together in grids, and then we try to make forecasts out of it with models. So what are the models that we are talking? So some people may think that this is a good model, other people may think this is another good model. Some people may think I'm a model. Just to see now if you were awake, but this is not the models that, unfortunately, I'm not going to talk about today. I will talk about mathematical models and numerical models, that they have one advantage compared to the others. They improve with age, okay? So we solve bugs, we include new formula, and this makes that these models are more robust and that they can do other things that they were not able to do before. So the model that I will tell you about today, that we are using, is called MOIT, that comes from the Portuguese Modelo Hidrodinámico, but then it was supposed to be an aerodynamical model, but then evolved in something much bigger, and now it's a kind of a family of models that include one for the coastal area, one for the water sets, other one Lagrangian particles. I don't know if you are that used to this concept of Lagrangian particles, but I believe that you all know. And it's since 1985, so it's quite mature. It still has some pains from being that old, and tomorrow there will be some presentation talking about it. But it's also a software that has been developed. Of course, they have a promoting team, but then there are many users in the world. Like this is another institution that they have used or use the model. This is not an exhaustive list because we cannot know who is open source, so anyone can use. But this is what we find in the literature, who is publishing things using this model. And then they have this coastal model that is, or open ocean model, storing that we call muddy water. This, of course, is the one that has more applications, normally more in Europe, less in the US. Maybe next year we can present more examples. But this is the most used. Even we have in all the continents. Okay, even in Antarctica we have one implementation. And then this is the younger model, that is the watershed model, but still is growing with time. So it's used for different things that I won't talk to you about it today. So it's even for precision agriculture or flooding events, rivers. So then this is built with a scientific background or with scientific production. So at the moment there are like around 130 MSc and PhD produced or contributing to the code, and more than 350 papers, journal and books. So we try to publish as much as we can or to document, but we know that it's not all as well documented as we would like to. But then coming back to what we want to do in the coast and how do we use these models in the coastal area and in some particular areas. Normally we have these global circulation models. This is one example. That is from the Copernicus Marine in Europe. You will have something similar in the US and in other places, where you have a model that is covering all the globe, and sometimes you have regional models. You can download this data, this is all open access. But then when we want to go to the coastal area, we need to do something that is called downscaling. That basically is that we refine the grid step by step until reaching the desired resolution for the process that we want to study. So depending on the process, we will need, and we can do this many, many times. Like this is what we do sometimes, that just to extract one window of results, then we nest a model inside of it, then another, and they run separately. So this is one example for the Portuguese coast near Lisbon, where we had like 35 meters because we wanted to study the pollution from some freshwater source near the coastal area or bathing waters. And then we produce some indicators and we can produce some alerts with it. This is on the horizontal, how we reduce the scale, but also we have to take in consideration the vertical discretization, and we can do many things. It can be Cartesian, it can be sigma. Sigma is very common in some models, but then it doesn't work well for everywhere, one kind of vertical discretization. So I'm trying to explain this because of the type of data you may find or Julia may find when want to represent the data. And then I show you this example from mainland Portugal, but we can do for any other place. This is some configuration for Madeira Island, where we can go up to 200 meters, but 250 meters, but I think it was because also studying a submarine outfall. We couple different models, so we have hydrodynamic, we couple with the atmosphere, and then also with biochemistry, and here we can see just the image from top and a vertical cut next to the island of Madeira. And then we can do the same thing here also here for the Azores, that where we are. So I would like also to show you a couple of examples from here that we do in collaboration with the University of Azores. And then we go from this large resolution and we can go even to this small one that is the level 5 with 80 meters between Fayal and Pico. We also need these very nice graphics that you do. So we would like to start also using Julia for this type of application. But then if we go to a global model, that is the only available at the moment for the Azores, that is provided by a big institution, I mean, by a global entity, this will be the resolution. But if we want to go to this channel here between the island of Fayal and the island of Pico, this is one cell. So then we need to do this downscaling to incorporate this bathymetry that we were seeing here, and here you can see a bar. I don't know if you can see here the point, no? Not here, okay, but you can see like a bar in the middle, and this bar has a lot of influence of what happened. So you can see it also here, and you can see it on the current. So for people that are crossing from Fayal to Pico by ferry, you can really feel this current. So this is the type of thing that we use this MOID model to solve some of the different resolutions. And then a different thing that we are trying to promote is changing the way we see the ocean, because normally oceanographers try to look only at the ocean and try to forget about the rest. This is how an oceanographer will make a plot, probably with Julia. But then the idea is that to integrate the whole Earth and move into what is called the Earth system models. So the idea is that we can integrate the water set, estuary, and open ocean, and as the water continuum, as is also known. But we have several constraints or interfaces that we have to solve them properly. But just to show you how it would be a graph from a water set model and how it works. Basically, it collects the water that comes from the atmosphere, and then through some streamlines, it goes into some channels. So this is some of the things that we graph that it will be also interesting for us to do with some of the packages or some of the code that you have. And here I'm showing one example for a dam in mainland Portugal, but also in the island you can have this effect, like today is raining here, but you can see an example of what Alexander was showing before of a real, one of the, I don't remember the name, the Von Karman stream. You can see it with the Madeira Island. So the island has an effect on the atmosphere, and then you have rain. So, and then you can have this application also with rain going into outside of the continent, normally when you think about freshwater contribution. So then we want to do all these things in forecast mode and automatically or operationally, how it is also known. And then we divide this in, I would say, 3 steps. One is pre-processing or finding the data sources, interpolating, making the data available, making everything in the right format, looking for different sources, downloading, all this stuff. Then we run the models. It can be different models. It can be the MOID water, that, as I told before, or the water set that is called MOID land. But also we can run Wave Watch from NOAA for waves, and we produce HDF5 files. This is our native format. And then we have the post-processing, where we distribute all this data and we do many things with the results. So we can go to a thread server or with OpenDAP, and then we have to convert into NetCDF. So this is another format that I know that you are all probably more used to work with it. We use this data for validation and to compare. We distribute in many ways. It depends of the end user of our product. So this is where I see Julia. I see Julia in the post-processing, doing graphs, or doing other applications. I will show you some of the graphs that we produce normally, or some of the graphs that are required to us. And also in the processing, because before you go into this operational mode of forecasting, you need to test the model. And you need to be sure that the model is producing the result that you want. And only for you to understand how an operational model runs, basically every day you have a new forecast. It's like the weather forecast. You are used to work with it. No? So every day, probably the people that are operating the meteorological forecast. They are assimilating the data from yesterday to have the best result possible, and then they try to solve the forecast for the future with the equations, now also with artificial intelligence, but they try always to improve the hindcast with this. And this will be like, for instance, how the Copernicus global model works. Every 15 days, they do the best analysis, then an analysis, and then every day they move forward 1 day. So every day you have more day. So how we were doing this thing before? Surfer, MATLAB, ParaView also, other software. Now we are moving to Python, but we are starting, so this is why it's a good timing for talking to us and say, yes, why don't you try Julia? Okay, so it's a good timing for this. And this is, but we don't want to use, especially MATLAB. MATLAB for operational, normally I get this error message because they cannot contact with the server and everything stops. And this is not very good for operational. So this is some of the graphs that we produce on a daily basis, especially the ones on the left. So these are the forecasts for today, we have different scales, as I was showing you before. So this is for the Portuguese economic exclusive zone. Not only, there are also other territories on it. This is our larger model. One for mainland Portugal, and this is for the Tagus estuary. And then also we produce other type of plots that are vertical cuts. And then sometimes we don't want to have a regular vertical grid because the biggest change takes place in the upper layer. So then we don't want to have a graph that is represent in the same size 5,000 meters than on the surface. So this is one of the things that is served for checking if the model is all right, but also we need to show this kind of information and to analyze the results. This is in an estuary in Sado, that is next to Lisbon. And this is another type of graph that we produce. We produce this kind of animations that I believe that we have seen many here. But you can see another particular thing here, is that we have tides. So we have intertidal areas that cover and discover. Okay, so the grid may change with time. And then also we would like to plot like a line on it, and then we use this also for validation. These results are pretty good, in my opinion. We didn't do any assimilation or any trick on this, and we were quite happy with the result. But then we can do this for different properties, okay? So that was for temperature. This is for salinity. And so this is something that we produce on a regular basis. And this is more like analyzing the modeling results. Another type of analysis that we do generally is like validation or comparison. And here you can see on the left, this is a month comparison between the satellite that was Moore, that is 1 kilometer sea surface temperature, with the modeling results, and then we do cell by cell correlation, bias, root mean square error, and try to see how it moves. But we do like this integrated in 1 month, and on the right, this is just for one day, because we have just one file per day. As you can see here is the validation between the satellite is on the left, and the model results is on the right. On top, the ones that we produce. On the bottom, the ones that are produced by the global model. So we use also to compare how our model compares to the satellite, how the model compares to the global model that we are using for forcing. Then, as I said, we are also looking for data. We try to analyze all the possible data. So this is another type of data that we use. This is called Argo floats. I don't know if you are aware of this. So it's kind of a sensor that it has like a 10-day cycle. It drifts in the ocean for 10 days at the depth of 1,000 meters, and then it goes down up to 2,000 meters, and then on the way up, measure temperature, salinity, oxygen. It depends on the technology. Now they are developing more coastal ones, so they don't go that deep, but they are also developing like deeper ones. So this information, there are thousands of them in the ocean. That is what also fits the global ocean models. And we need to compare our vertical profiles with the vertical profiles that are coming from this type of technology. And we need to do this kind of Taylor diagrams, this kind of temperature salinity diagram, this vertical profile diagram, and compare between them. And then we have other technologies, like this is a glider. Then it's different because then we are operating it, so it's moving. This is a mission that we did here in the Açores, next to Fayal, and then you can see it doesn't go to the same depth of the time, and then it's moving in location. But then we need to compare this data also with the global model because we want to do how we perform and also with our results for this area. And there are others that I won't talk about, like HF radars, that you have currents on the surface. So we are always looking for all the information because it appears that there is a lot of information, but there is not that much. And then other type of products or graphs that we do is when we talk about these Lagrangian models, that Lagrangian models are like, instead of having a grid, you are following small volumes of water. That the volume of water, or it can be a volume of water, or it can be different stuff. It can be a container that is drifted by the ocean, and this type of technology is very useful for search and rescue operation, for oil spills. So I will show you one example here from the Prestige accident in 2002. This one of our first forecast, because it's 2002 operational oceanography was still, giving first steps. And we compare with satellite images, and the model results are pretty good. This for the time, we lost money because our servers were not ready to provide so much information in real time, but then we recovered because we were able then to be involved in many projects related with this. And this is one of the latest versions that we have from the Lagrangian model, and we use it for marine litter. Now that is kind of a hot topic, so we can put so many rivers, 61 rivers discharging, and then because it's the main entrance of marine litter, and then try to see where each river, each marine debris from each river will go, which are the area of influence of every river. So we can identify river by river, and then we can perform this model was reshaped and is very, very efficient in terms of computing. We are running this sometimes in laptops or things like that. So you don't need a HPC for this model at the moment. Other way of doing this or graphing this is like, instead of putting the discharge from the rivers, it's like putting all the data or filling the Atlantic Ocean with these Lagrangian tracers and see where they tend to accumulate. Okay, so this, for instance, we can see that mainland Portugal, we don't have a big problem. Probably in the US and the Caribbean, they have a bigger problem than us with this. This is, and then when we want to represent, it's more not to analyze the result, but we want to represent sometimes what you can see behind are the currents, and then each particle with the origin. So this is the type of information that we use. But when we go sometimes to policymakers, they don't want this information like this. Yes, this is too much information. So we want to integrate this information into a grid that we have defined, and we want this in a shape file because it's what we use. We don't use NetCDF. NetCDF, what is that? So they want to move into shape files, so we need to deal also with other type of formats in order that we can provide this information. This is another example that we would like sometimes to integrate in polygons. Like this is one example also from the Azores. there is a marine protected area, and they want to know the temperature in the surface, or 1,000 meters, or just along the bottom layer. Okay, so it's looking for what is the first cell of water and representing all along. So it's not one layer of a grid. It's looking for every cell, the volume. And then, as I said, we produce sometimes NetCDF that go to thread servers, and then we can make this, we can distribute the data in this type of format, WMS, and it's very nice because you can see the streamlines and everything, but this is good depending on the end user. This is, if we have a control room like this, it's a very nice platform. You can play with that. But sometimes we are working with people from aquaculture. So this is their office. I don't expect them to do many clicks on the platform and to select properties and everything. So then we have to prepare the information in a way that is readable and easy to understand. So then we process the information in a way, I won't give you too much detail about this product, but we have set up this kind of graphs that are summarizing all the information, and then we can distribute it through Telegram or through WhatsApp, and then they receive it on the mobile phone. They don't need internet anymore. They don't need to click, and the idea is to concentrate all the information that they have into one graph. So this is something that we need in terms of production. So this is the kind of example of the type of things that I can imagine, and I imagine doing this personal brainstorming during this couple of days, that we could do also with Julia, or that some of them we can start little by little. But as I said, I have a challenge for you. Because numerical models, and now you all learn that, improve with age, but support tools get older. And this is a problem. Because then you develop something that works for Windows or for Linux, but it works for Windows 7, not for Windows 10. Everything is changing all the time. And also Linux is changing all the time. Everything is changing all the time. So support tools are very difficult to maintain, or is a bit expensive to maintain. So my challenge and offer is that, okay, coming back to the first presentation on Monday about if you develop something during 5 years and then the person at the end doesn't want it and you invest thousands of dollars or euros or millions or whatever, in this case, the community of the end users, we know what we want, okay? So we won't change that much what are our requirements. We know, as you can see, what are the type of graphs or the type of tool that we want to produce. We know what are our formats, and you don't need to program something that is able to read now a value, now a name, now a vector. No. It will be always the same. It will be always the same file with different information, structured in the same way. Very boring, probably for you, but it will be the same. But so there won't be this waste of time and money and resources on using user and developer feedback, and the user satisfaction will be guaranteed. Also, we can also provide this access to the modeling community. So if we start producing something in Julia, in this sense, we can also distribute it along with the model binaries and code, and then this may be an entry for other people that are working also with IT into practical programming with the Julia. So at the end, you will gain more Julia users, which I believe that is a jackpot for you. So I'm going to show you what is the tool that I want to replace, because now it works randomly. Some computers work, others don't because of the graphic card or because, okay? But I will show you, and I will show you the capacities, okay? So I'm going to open one file, HDF5. I can choose one day. It can be the day of tomorrow. And then when I open, and I do this on a remote computer because my laptop doesn't work. Okay, so it's a real need. I'm not making it up. And then I select what is the latitude, and of course, the code will be. And also I was thinking about this yesterday when I seen some of the presentation like Mikey, that you have also buttons and things like that. I mean, it doesn't need to be a self-contained software, but it could be one of the. And then we can also put the vertical profiles, and then we choose, okay, we show temperature. And then we select the time, and then we run. Okay, so we can select the color, and we can normalize. And so it's between 0 and 1. Up, to make it bigger. Okay. We can zoom. We can pan. We can change automatically, like, okay, instead of normalize, I want temperature between 10 and 20. Okay, so this is very useful for us because when we are starting a model, if the model breaks, have a problem or anything, we need something quick. It's not for making an image for a publication in a journal. Even, I mean, it's not that ugly. But this more for something that is rapidly opens, then I can analyze, then I can see, okay, what is happening. There is a problem in the top layer. Okay, I will see the top layer. No, it's not the top layer that the problem was. Okay, so I want to change the region of interest. So instead of being this cut, I will do another one below. And then I can see here, okay, but now this seems okay. So I will change that one, and I will put more near to the bottom. Of course, you can see here is recognizable, but you can see here some sea mountains. So it's doing this vertical cut, but we can do vertical cut, but we can do also, we can select, instead of horizontal layers, we can these vertical cuts, okay? Then I can change the relationship between X and Z, because if not, I won't see anything that is properly understandable. Oop. Maybe it's too much. I will leave it like this at the moment, okay. Okay. Well, doesn't matter. I have one open here also. What is the best we can do? Even we can do like 3D and add in different layers. So we can rotate. You can see the bathymetry here. I mean, it's similar to things that I've been seeing here. I mean, that's why I believe that this may be easy for you. If it's already uploaded on the Google Drive. There is an HDF5 file. Okay. So then, I mean, you can see that you can add layers. You can add horizontal layer with vertical layer. We can see on the 3D, and then we can also here. I mean, I'm not making the most complex of all, but we can put also Lagrangian particles here, so we could see how the particles are moving if they go from the bottom of the ocean to the surface. We could see with the instance how it works. So, and then I can move the time, change the scales. So it's interactive in the sense that it's not a plot for distributing for outside. It's a tool for analyzing for the modeler. So it needs to be fast. And sometimes when we use ParaView, we can produce very nice graphs, but we need to do many clicks, to see the file, which is. So we were thinking this is a tool that it was developed by this group in the university, but it's no longer maintained. And then we are trying to recompile it, so then we can keep using with the new versions of Windows, at least. But it's not being very easy. So at the moment, what I do is that I know some computers where it works, and then I use it there, and I don't use it in my laptop, for instance, which I know that it's not the best practice. So that's why I bring you the challenge, because what I have seen in your presentation is not very different from this. Okay? Then I was thinking about it while I was doing this personal brainstorming and talking also with people from AirCentre, saying, maybe Thursday afternoon in the expert hour, we can try to talk about it a little bit and try to put some, because this, I mean, that would be very, very helpful. And I understand from your presentation that this is probably not the sexier thing that the Julia can do, but it's really a very useful tool for us. So I leave the challenge for you. Maybe tomorrow we can talk at any time. I'm here for that. But also, if you want, we can tomorrow in this expert hour we can talk more into detail. But if you want any detail before, or you have other ideas or how we can do this, I mean, I'm very happy with that. And well, that's everything I have to tell you. If you have any question, that's it. Thank you.
I do have a more technical question regarding how you did the ocean modeling. Did you do, is it like downscaling from the ocean company service? Like you took the data from the marine company service and then down it to fit like around the Azores for your ocean modeling? Sorry, I just wanted to ask. I just wanted to ask for like how you did the ocean modeling, because I'm interested in that as well. Like, did you use like open boundary conditions, and then after that, the data used for open boundary conditions was from the Copernicus? Yeah.
So yes, I can explain you more about how we do the modeling. I didn't go too much into the details. But yes, basically what we do is, I mean, our recipe, that we take these global models, we put it on the open boundary condition that you can see in this case is all these areas and then we relax this result inside of the model. But then we have methodology. So sometimes we use GFS from NOAA, but sometimes we use IPMA, high-resolution models, depending on what we have. And then we also look for river data, that it can be from a model, it can be from observations, and then this generates the solution inside. In this model in particular, is running free. So we have all the equations working and that. But some other people do more assimilation, so they refresh the values inside of the domain after a certain period. But yes, what we do this downscaling thing is to go from these global models, use them as boundary conditions, and go into the coastal area. Welcome.
Super nice presentation.
Well, thank you very much.
My question is, how confident are you applying this downscaling assessment from the global model to the Azores? Because it is one thing that it has been really hard for us to try to work with these global models, because there's none for the Azores.
Yeah.
No regional models. So how can improve? Or how can improve?
Yeah, the best thing is to have more data. This is always like a good bathymetry always helps. high-resolution bathymetry, and also observation. And we were last year in Fayal during this course of, with MIT, of a course, MIT Portugal is co-organizing a marine robotics course there, and we have some validation there, some direct and some indirect. The direct one was like, okay, we found that there were some tidal ghosts. We compared with the model result, and they were very nice. I mean, very, very good. The indirect one, there was one guy with a wave glider that had to come back because he has a problem with communication. And the guy was in the same place where we were, and I was telling him, look, take care. If you want, and I think you can even see here in the figure, so this is the port, it's just in the southwest. Okay, this entry there where there is this mountain. If you want to enter here, you better go by Pico, because the current is very strong up. So then you go up and then you go down. He didn't believe me, so he tried to go direct and has to cancel because the current. So then there was also, and I was telling him, okay, look, this is the best timing, the best time of the day, and if you want to do this, I will do the operation this way. And then, no, maybe he received other instructions, but then he tried on the approaching the coast from the other direction and has to come back. And then he managed afterwards. I said, you were right. Yes, I don't want to be. Yeah, so, but the comparison that we are doing, of course, we are trying to collect more data because it's important, the quality of the data. But we have done this in many places, and the results are, the better the information that you have, the better the result. But in general, it works well. Yeah, that's why I said that we are unfortunate that we have to understand everything, because we are looking for remote sensing, tidal ghosts, whatever kind of information, ferry boxes, like ships of opportunity, whatever people that goes out there and collect data, we are always looking for data to compare, because in some places, even if we are sometimes close to the coast, and there are estuaries where there are no observation in near real time at all. So then sometimes we have to look for historical data, simulate that period in particular, and sometimes even, and then we have other problems that maybe also with, there may be other problems also with the meteorological forcing. Imagine that we don't have a good meteorological forcing in the area, and the meteorological models has their own errors. So, but in general, the results, they are, I mean, the comparison that we did, they were very good. So, okay, thank you very much. So I will be here until Friday, if you want to make me a surprise.
Okay, thank you very much. We'll now have Mr. Joaquim Luís doing a presentation about Earth observation mapping and exploring with GMT.jl. Joaquim Luís obtained his PhD in geophysics in 1996, IPGP, France. He is currently an auxiliary professor at the University of Algarve. His research interests include marine geophysics, namely North Atlantic marine magnetic compilation, plate cinematics, tsunami modeling, and scientific programming writing and development of visualization tools. He is a core developer of the generic mapping tool since 2008, co-author of the GMT MAX, GMT MATLAB interface, and and Swing, a tsunami modeling tool in C. He's also the author of the Myron, that is a MATLAB GMT GUI for Windows, and the Julia GMT.jl and Remotes S.jl packages. Thank you, Joaquim.
Oops. No?
Usa o adaptador. Não é? Vais ligar aqui. Pela
Mas deste não. Deste não. Ah, aí, meio.
Aqui. Agora liga aqui no teu.
Aqui, deste lado.
Deste lado?
É.
Pronto. Já está, já está.
So, hello all, good morning, especially for the ones that are not here. So, I'm going to present, I've been watching and participating on the Julia community for a long time, but this is actually the first time that I will present what I've been working for in Julia, which is this wrapper to the GMT tool. GMT, for those that you do not know, is a very well-known in this, especially in the geophysics community, for a long time. It actually started at the end of the 80s, but by the time to PhD students that named it GMT after the gravity, magnetics, and topography, because that's the things they were studying, and at that time there were no tools for making maps, nothing. So they started with that and later changed the acronym to mean generic mapping tools and make a point to make it generic all the time. But the figure that we are seeing here was produced in 1991 with a postscript that had started at that time. And they were able to make that plot, which now seems trivial, but I repeat, it was made in 1991. And it made the cover of, some of you might know, the HGU journal EOS. So that's when I learned about GMT. I was doing my PhD at the time, and I only knew a bit of Fortran, and then I needed to drop some magnetic anomalies on top of topography, and GMT did not do it. And well, I was stubborn enough to learn a little bit of C, and was able, without really knowing how, to make that tracking at that time. And that's how I got involved in GMT, you see. And a little later comes the Miron thing, which is a MATLAB GUI, that because with students I tried to teach them GMT, and I was not successful. Oh, no, okay. In the Google Drive, you have two notebooks, or two versions of the same notebook. One empty, and the other one that you can run. But because there are some issues in the middle, I already run all the cells to not have any troubles in here. So that's what I'm going. So you have both. You can just follow from the screen or execute them. GMT has very little direct dependencies. One of the reasons he has very little dependencies is because GMT itself, the library, already have most of those dependencies included. So since I think 2008 or something, Canal was included in GMT. So when you install GMT, either the Julia wrapper, via the Julia wrapper or the library, you already get all of those. That dependencies that gives access to read almost those formats, the raster and vector. So most of the things, I don't need to include more extra dependencies via Julia because they are already accessible. But start with, I don't need to increase the font. That's not the point. This is the example on modern GMT, what you have to type, to write to make that figure that I just showed. So GMT is very, and with the time there's options to do everything. But it's very condensed. So you do an option normally with a single letter. And you have to type things like, if you see -N, -C, -P, -R, this is all the instructions to do the commands. Well, it worked well for many years and for people that learn GMT this way. But in modern times, people are not really more available to learn this type of language. So I started because of the two things. The other GUI from MATLAB, I wanted to port it to Julia. That's what the main reason I started with Julia. I'm still waiting for deciding what the graphical thing. It's a bit of the same purpose as oh, now I forgot the name because is that he asked it for the HDF viewer. Is this a bit of the same thing that I also want to do with that one? But meanwhile, and also because I think people in GMT core users could profit a lot of using this way of making the same maps and processing things in GMT, I developed it for a long time, the Julia wrapper. Julia has a couple of 3 or 4 types, which are simple types. Grids, images, datasets, polar maps, and one that's used but not by the users, the PostScript. The types, which are not briefly, they are described here, are simple types. They are either matrices, well, they are always matrices. Is it either a grid or an image or a table? They are matrices of the same type. And then you have other fields for metadata. So you can have georeferencing and other type of information in those types. And those types derived from the previous work that was done to a MATLAB-based toolbox in which you can communicate directly memory from the data to MATLAB memory and back. And that thing was sufficiently close to what Julia does that I could port it more or less one-to-one, although with a lot of work, to Julia. So we communicate directly from in memory without writing temporary files. And the GMT-C code has certain internal types that are mimicked by this one. So that's why they are the way they are. We have a type for a grid, a type for an image. In MATLAB, in GMT, we distinguish between grids and images. Images have colors, grids have whatever information, temperature, the bathymetry. So internally, the distinguish is made. And then I extended a bit some of them, the data sets that added attributes via dictionaries and things like that, and then georeferencing. But it's a more limited type that you get, for example, for data frames, which are also supported via weak dependencies. But you can have attributes, you can have all the referencing, you have the geometries, you have all of those things with the limitation that they all have to have the same data type. I cannot have integers and floating points in the same type. So in that regard is a limitation for broader use, but for GMT internally it is not. So a couple of examples. The grid type, and well, those types, they use the array, it's written here, the abstract array interface. So it means I can simply, with a grid, do operations like this one, small. Say I have a grid, I want to calculate another grid, I have 1 to 2 times the other. So it's just not only do the same operation with the matrix, which is trivial, but you also have to update the metadata that comes with minimum, maximum that is used later. So, but for the user, the only thing you do is you do these algebraic operations with grids or image as you would do with any matrix, and the internal machinery of the types takes care of updating the things that need to be done. Okay, another thing, figures here in this notebook are large in this on others, because another thing of the particularity of the GMT, it produces PostScript, and it works in a layer cake model. So you have one layer with one thing, and you keep adding things to that image file, whatever. So it means you can do a lot of very detailed things, and you put them on top of the others. But that means it's not interactive. So this is, you produce, call it static images. It's not interactive. For example, one consequence, you have to define our domain, our limits of our image on the first call. Because you cannot come later and say, okay, but this data set is larger, let it automatically expand the axis limits. It does not work like that. I have first to know what is the limits and then create it. And the other thing is the plots in GMT, which are produced PostScript, that later GoScript converts the other raster formats, GeoTIFF as well. The units are centimeters or inches. It's not points. So you define the size of a figure with centimeters, and you can go up to 11 meters. If you want to make a figure with 11 meters, you can do a figure with 11 meters. Coming back to this, I am not able to make smaller figures in the notebooks. It decided to have the largest, the width of the screen, and the figures are a bit too big. I would make it smaller, would be nicer, but I have no control on this side because it's the Jupyter that decides to make them like this, and I never found a way. When I have images with pixels, I can say with 50% or something like that, and it obeys. Here, it does not. So this figure by default is 15 centimeters. You can make it as small or as big as you want. When you make them small, those who have experience, you know that then the labels start to coalesce. There is internal algorithms to try to guess the size of the text that still do not overlap, but if you make it very small, it's impossible. So this is an example. Oh, another thing that's my preferred taste for users, I try to make simple figures possible to be done with a single line. So I made many gymnastics. For example, in this one, that is the peaks function that people use MATLAB know about it. This is the same one. And then you make an image. I have the color bar, and I have the contour, default things. So the contour, for example, I could set the thickness of the contour lines, the ones that are annotated, the font of the annotations, the colors, the left, all of that. But to do that, you have to use the function contour that gives access to it. But because most of the times what you want is just a quick and nice one, you have those versions as well. So this could be much more elaborated, but would not, of course, take only one line. If I want to make it 3D, it's 3D in perspective. The GMT is not 3D, it has no volumes. So you cannot do a volume figure. But you can take a surface and make it in perspective, like this one. And again, I try to make it simple. Let's say the viewpoint, and automatically has a default height, which is 6 centimeters or something like that. Again, you can change all of these. But using the defaults allows us to say, okay, I want to see the perspective from, this is azimuth. So under 35 means under 35 degrees from north is an azimuth, it's not a mathematical angle. And you get figures like this. Also, shading is a very useful operation that when you want to look at data, because when you do non-shaded images, things look good, but if you have noise or other troubles in the data, the shading is a very powerful operation to show it. So I got the habit of using that almost all the times. Images as well. You load an image and plot it. This is just a JPEG image that comes with the test, so it's reproducible because it's on the test data set. I got that one for the next figure. Found it in the internet somewhere, because you can also plot them in the sides of the cube. This is a half finished work, because my real intention is to be able that instead of having the top one, having a surface, the surface will go, will not be flat, and I want that the figures on the sides of the cube would follow that surface, and it means in this case I would have to clip it, the gray areas. But okay, if you want to plot them in the sides of a cube, it's also, this is already kind of an extension. It's all done by GMT, but the commands that would have been necessary to do all of that would be a lot longer than just this one. You say cube plot, you give the 3 images, and by default it does that. If you want to just put some of them, it's also possible, but you have to consult the manual as normal. Vector data. Again, as I said, because Canal is already a dependency of GMT for many years, can read the vector data, OGR vector data directly. So most of them is concentrated, I would say, in this GMT read function that reads images, vector, whatever. It decides that by but the extension when it can. Otherwise, there are keywords that you can add to help it. It's a grid, it's an image, it's an OGR, whatever. So the most common ones are detected automatically, can even be zipped. And if you load this one, this example is something I saw from, I think from a tutorial from R or something doing some data science in Colombia. And well, I decided to try to see how I would do it with the GMT. And okay, it's this. Just read the Colombia shapefiles. It plots, the show method shows some information of the data set that we get when we read it. You have the geometries, you have the projection, the referencing information, shows some of them. And, okay, again, there is one image. We also have a viz function because I'm also a bit lazy. The less I can type and it's still readable. And so I think it was Julie that first came, but at least that I saw a viz function and, sorry, I pirated also. You can say EM show like you do with MATLAB, you can say viz, you can say others. But this one is really short and it is nice for this. So, and this is quite a bit for what MATLAB does, is projection. This case does not require that much because, as you see, we are at 8 degrees of latitude. So at close to the equator, you don't have much information. But when we go up, when you go to Greenland, if you don't do projections, you get a very deformed image. So projections, when you do maps, is something I think should be present all the times. This one here, when you say proj, well, proj equals guess, it means because it knows the region, it knows the referencing system, it can go at least directly from geographic for the other ones, and it decided the projection that he used. Probably use it Mercator because it's close to the equator, but he uses different projections, we'll see, for other regions. So this is a projected map of that shapefile. I'll stop the examples here. We can filter with the filter. I overloaded the filter function in Julia, and you can select the name of one of the departments here. In this case, you say here filter name equal Antioquia, and you get the polygon that contains only that department, and you can paint it with, it's in Julia and the other ones. So it's more or less the common names. You have the fill for the color. Well, you have title, and again, the projection, and you get things like that. So, briefly, there are lots of drivers in Canal. The list you see here is the list that you get from the Windows installation. It's very close of what you get from the artifacts that you get from Julia, because the number of drivers are almost the same. Perhaps a bit higher in Windows because I build this frequently and I use a lot of drivers, but say you can have the list of all the drivers you can have for the rasters. That is not an exhaustive list. Alexander mentioned ZAR. I never use it, but it's here. Many of those things I never tested. So, like it happened yesterday with this, we tried to load complex array through this. I got an error that probably was because of that is not accounted. So, in several of them, for sure, if you try that, at least the ones that I did not test, it's very difficult to put tests for all of those things. You need files, examples. So, yeah, sure.
Just curious, like when you send that projection keyword to the viz guess, what is the heuristic that you use in order to guess the projection?
I saw what happens.
Okay.
And I can show you, there is a function that's called proj guess or something, that more or less that's the name, and depending on the latitudinal extent, it selects between 3 or 4.
Oh,
so
got
that's
it.
Lower latitudes, traditionally, especially in marine things, we all use Mercator, and we use Mercator even when we should not use Mercator. So traditionally, I keep using Mercator in Greenland, which is not a good case, because the deformation of Mercator grows a lot when you go up to 50 degrees is still a little bit, but manageable. But when you go to a very high latitudes, then the deformation is very high. So there is a function with 3 or 4 that looks splendid because this is especially by latitude.
Yeah.
So there are 3 or 4 projections that it pre-selects and it generates the broad string of that projection applies it.
Got it. Makes sense. Thanks.
If you want to make a global map, you would do this. There are many. Maybe I will do a projection. If I want to use a Mulwave projection, I would spell it like this. Set the color. GMT comes with its own database for coastlines. It's a very detailed one, old, detailed, and old pays in one thing. Because it was made in the 70s, last century, it uses a different data. So if you scale down sufficiently to see the difference and compare with satellite, you will see an offset of about 300 meters something. So if you go to that scale, you see the, but otherwise, you have this. And because it was done at the time that the computers were, we don't imagine how, those 90 megabytes of NetCDF files were compressed, made in 2 integers and 2 bins and to scale. So this could be done 30 years ago with the same resolution that you can do now. So these are not polygons. These ones are line segments that are joined and filled. And there are several tools to compute masks, many tools that use this database. There is another one which are polygons that came from the DCW digital chart of the world polygons. That it's an alternative, and those are polygons with the countries. So, what comes next? So it also has states from the biggest countries, rivers, maritime boundaries. This is an example of plotting the Americas, north and south and center with the countries, the states, and this blue is the maritime boundaries. I don't know from, it's probably, no, not Hawaii, no, south, don't know of one of them. Not very interesting for me. If you want to do a Lambert equal area projection, do it like that. More, okay, more, I think. Another thing that GMT uses, a lot of them use the physical. So the GMT servers, no, they are, no, that's not true at all. I even had one in my university. There's not able, but you have other servers have copies of the same data. I have a collection of, not so extent, but perhaps I have to swap a little bit. Data sets with these things. You have the seafloor age, you have the geoid, oh, it happened yesterday. I don't know why. Huh? Okay. Mean sea level, several, the ETOPO, SCRTM. We have SCRTM up to 30 meters. Because these are very big files, SCRTM for the whole world at 30 meters is 45 gigabytes. The server has those files tiled depending on the resolution, and we can ask to download them directly. This is what you can do if you run the notebook, but well, it might not take that long because it's a bit like we were saying from the NetCDF that you define the limit, you only download the bit that interests you. You can have those are pre-prepared, were filtered with very good filter that when it filters by distance, it knows that it's filtering a geographical quantity. So when you go up north, your filter has to extend east-west because the degree of longitude and latitude will not cover the same distance. So these type of things are very detailed and well implemented for a long time. And those data sets are filtered at different resolutions. If I ask, for example, again, I say the gas, shade, no. First I downloaded this one. And they have a naming, which is simple, Earth relief. One is for Earth. For the other planets is other names, and then the resolution key. This one, 05M means 5 minutes of life. You can go even to the seconds, depend on the data set. For the Earth, you can go at 1 second, which is 33 meters. Of course, for that one, you are not interested in anything larger because you will wait a long time for the download. So If I do this here, GRD cut, well, it says GRD cut, the name of the data set, and a named region. Each one is IH023. Hydrographic Institute has named regions, and you can also call, instead of giving, you could give a limit in geographic longitude and latitudes, or using named regions. I use the named region to download this one. So see, the command is GRD cut because it will cut from the global one, these limits, and creates a grid type, and I only have to say again, show me the picture with the grid type, add shading because it looks good, and in this case I did not add anything more. So, and you get a map like this. Next one thing is the Azores, where you see the quality of data is of course no longer so good, but that's what's publicly available for the bathymetry or audio source. This one is the same thing, except that I use a smaller limit around the islands, and I added the coastlines painted, so well, to help us localize better. It doesn't, oh, another one. You can also use the facility that we have nowadays that when the data is publicly available, for example, to make seismicity maps. There's a function that's called seismicity that by default gets the last month of the seismicity as provided by the USGS. You can tell this, you can control this by magnitude, by date, period, can be a week, can be a year, can be many things. The default is 1 month. At the end, this is a legend. Legends and GMT are very detailed. Not so easy to do. The default ones, yes, but if you want to do something very specific, you have to read the manual of the legend command that allows to do things. This is a legend. You could put this a legend in other plots. In XY plots, you can put also legend easily just by saying legend equals yes or something like that. You get the defaults. When the defaults are not good enough, then you have to go to the model that does the legend, and that one is not so easy, so simple to use at the first sight. So you can do things like that. And this is very recent because GMT 6.5 was released officially, I think, Monday. We don't release that much, and it takes time, and then last-minute bugs are always delaying. And while it was not released, the other planets were not available. Now they are available, and instead of asking for Earth, I can ask for Mars, and I added the coastline of Earth on Mars so as to localize, help us localize, and the Mount Olympus would be here. Well, see, you have the US coastline to help us. So you can do Mars, Jupiter, no, of course, Mercury, Venus, Moon, and Pluto. Pluto is out. No, Pluto is not complete. Pluto is only this. The satellite that passes there did not cover the entire surface of Pluto. See, Pluto is only this. But you have here Moon, Venus, Mercury, Mars, magnetic anomalies, global magnetic anomalies, and well, the collection is not larger than this. But these ones are provided by GMT, tiled, and very handy when you need it, especially the bathymetries and topographies. So, again, if you want to see it in perspective, you do the same thing, which is nicer than the first example. Then you first see, you set an elevation, azimuth and elevation, and you give it, well, that and say shade. Again, I cannot plot so easily the coastlines on here. I would have to do more operations. Because it's perspective, I would have to get the coastline, interpolate the grid to get the Z, and then I could plot that line on top of topography. But if the line only has 2 dimensions, I cannot plot it on top of the surface automatically. Well, I can write something that under the hood does the operations, but that's what would have been necessary to do in order to put the coastline in a perspective view. Oh, I talked at the coffee break with Simon. I also have a mosaic function that does what MapTiler, similar to MapTiler. It's not a duplication of efforts. I had that in 2018 MATLAB. And it was not ported. It's a code that at that time downloaded Google Maps, Google Image, what we now see in Google, and Bing. The problem with the Google is, by their terms of use, we cannot use them, even if you know how to use them. But Bing does not have that restriction. So by default, what this mosaic does is to use the Bing service to download the images, which are, depending on the zooming level, is satellite data or aerial photograph. One is high resolution, is never satellite data, it's always aerial photographs, which, by the way, are provided by the countries, free to them, and then they have terms of uses, they say that you cannot use them. Well, fortunately, Bing, from what I read, did not have that restriction. But to use them, you need to tell it where you want to have the things. Again, Udal came to the rescue because he has access to free server that gives us a geocoder. So, because normally you have to have an account, have a key, and to ask for a geocoder. Udal has two. I only tried it once. So that's what I use in this. Where is it? Geocoder function. Yeah, is where? Yeah, geocoder. What did I put? Well, the address of the hotel. Hotel can call. Angra do Heroísmo. I had to help it a little bit because my first attempt, I landed on the north side of the island. Apparently there's another caracol there. And, so I have to be a bit more specific on the address to get here. So I typed the address. I got the geolocation of and then the next thing is to tell it, mosaic, give me the image. There are more than one ways of using it. Also, you know, these images came in tiles of 256 by 256, and the resolution depends on the zoom level. So either you give it the limits, and it finds the resolution, or you give 1 point and say the number of tiles around. That's what I did. With after some attempts, I said 7 neighbors is enough at zoom level of 19, and we get the best that Bing can give us at this hotel. I can tell you, Google does better. It not does better. The images in Google are 1 or 2 levels higher than this. Can do the same for the island. Just say, this one I can say Terceira, just an MOO, to get the bounding box or the limits of the island, and you do the can project this image. They are projected. Oh, are they projected? Yeah. Yeah, yes, they are projected. So, because they are referencing, we can use the projection machinery easily. You can specify the projection you want. I normally use the guess because what it gets is normally good. But if you want another one, you have to give the parameters of the projection to it. Also use is tile provider. So you can use tile provider. Tile provider has a lot more, is a significant number of providers of mapping tiles options. So if you use tile provider, you can use the output of the tile provider, the type of the tile provider, and use it to make those images through mosaic. It's not particularly good, but I did not want to use the default, fortunately, because Simon also used it when the default is the night, day and night. That's the group I get by default. I searched it. Another one is meteorological information. You have lots of, this one is really, you have to consult the map tile manual because you have really a lot of options to do the things you can get. You also can easily, OpenStreetMap is straight almost for the mosaic, but these ones that have a lot of them requires more work from the user. Okay. Time. Oof. Another package that's separate because you have different dependencies is for the remotes. I call it remote S for remote sensing. And I use example. Well, when I made the presentation, I did not know about the Google Drive, so I had commented the things that you uncomment to download the data. But the data are Landsat 8 scene. Each band is about 80 or 90 megabytes, so it would take a lot to download. They are in the optional folder in the Google Drive. But there is also what is going to be used. You can with the for those that you don't know, the Landsat comes with what we call the scene. It's bands between 1 and 11. And all of those bands. You can download them all, or just some of them. And it has also a file with parameters for doing corrections. It's an MPL file that you also need to have it together. But it's a large, there are 200 kilometers by 200 kilometers at 30 pixels resolution gives something relatively big. So you can concentrate and say, I only want a chunk of that area, but you have to give it the limits and create a cube. That's what the commented part here does. Cut cube, say the least bands that you want, a template to not repeat that very long name of the files, and then save that in a GeoTIFF cube file georeference. That's what was done previously, and I load that cube. The report bands information gives the names of the bands, the wavelength, and so forth. And for example, you want to compute the temperature. The temperature coming digital, this coming digital numbers, you have to apply an equation. But some of the times it's just a straight line transform, other times yes, a bit more. Don't remember. This probably. But you have to transform that. That's what this dn to temperature does. So you give it the name of the cube, say the number of the band, and you get the temperature. I also added, this is the region of Lisbon. I use that for other things because along the Tagus River there are agriculture, and you can see very good examples of how the DVI and DVI index works well for this region. So that's why I like to use this region, especially because the river, the Tagus River makes that. But this is the temperature. I digitized 4 points here. I have to resample. I use a GMT model to do that. The resamples use the accumulated distance along the track. So you create the track, and then you can, there is another model that called GRD track, that you give it the track, XY positions, it reads the grid, and interpolates along those points. The shape of the line can have any shape we want. And if you do this, and you get this profile, temperature versus accumulated distance along the track. Not mentioned. Those two spikes are not outliers. Lisbon people, what they are, can guess? It's the bridges? At the bridges, exactly. Exactly. You can see them. You can see. If you come back, you see. There is the older one, and the narrow part of the view is the old one is the narrow bridge. It's the one that is looked like the San Francisco one. And the newer one is longer and has more length, so it's larger. And you can see the difference in temperature between the asphalt and the water that is below is sufficiently clear that you see them. So this is not, they are not outliers, are the temperature when we cross over the bridges. Using that cube, you can make easily, when there are not many clouds, a true color image. You just say, I have the cube, it has all the information that it needs, it stores the information from the MTL file with the parameters to do all those informations. It's stored as metadata of that GeoTIFF file. So if I want to do a true color image, I just say true color and the name, and I get this. This is one that works well. Sometimes it might, because it's automatic, that's the point. And I'm going to show what is done actually. You can calculate also what is called the radiance on the top of the atmosphere by a transformation that you can do with the parameters that come with the scene of the Landsat. And if you do that, for example, this one is for the blue, yeah, the anti-radiance band name blue, so it's for the blue band, and you plot it, you get this. I still see a little better. If you are looking here, you see very light. You see almost nothing. Why does that happen? For those of you that know how these things work, data is acquired with 16 bits. And you have 65,500 something possible digital numbers, which are not all used, by the way. The clouds are more in one of the sides, but most of that interval is still not used. And when you do automatic conversion for an image, you have to compress that integer 2 to integer 1. So it means from 65,000 something to 256. So if most of that is not used, you will have only the lower numbers, and then you get a very dark image. So you lose your dynamic of your data like that if you do it. If you just do it raw, you get an image. It's very dark, almost black. So what you have to do is to find what is the interval where data lives, and then take only that interval and stretch that interval, not stretch. So we say contrast stretch, But in fact, when you reduce it to the 0 to 156 interval, you only use that where we have that. Well, this is a nice behaved one because sometimes when you have clouds, you might have spikes, and the automatic thing might not work. In that case, you would have to use the histogram model with the numbers that you manually would have to give it to make it work. But when things work well, what it does, it takes this and automatically, if I stretch histogram, now I have this. It's the same one, but now we can see. Just one band, so it's preferably to show it on grayscale, but this is the blue band. And what the true color does is it does automatically these 3 bands, it can compute a true color image. And I don't know if you can see the difference. If I put the raw and the radiance on top of the atmosphere side by side, can you tell the difference, anyone, between the two of them? It's not big, but I think I can. That one's sharper, that one's better. Yeah. So it's worth doing the atmospheric correction. It does not take much, but this on the left side is the raw digital numbers, and the other one is doing the same thing, but using the radius in top of the atmosphere. In fact, there is even the reflectance of the surface. You can have models to compensate more elaborate things to do for compensating the effect of the atmosphere that supposedly work better and is not difficult to implement. I will do it at one point, but I have no need so far. Can also compute the NDVI. NDVI is very popular index to find green vegetation in green state. It relies on the behavior of vegetation between the red and the infrared. If the vegetation has water, it reflects a lot in the infrared and it does not reflect on the red. So based on that, they have been invented. Many indexes invented because there's no theory behind that. It's really attempts, trials, that people have done that. Where is it? NDVI is NDVI is simply infrared minus red divided by infrared plus red. The N is from normalized is normalized vegetation index, difference vegetation index. And it has a particularity. If you take only the values above 0.4, more or less, you get the vegetation that is in the green state. So, because the equation is simple, Julie is just programming this, yeah?
So very interesting in the true color and the NDVI. So I see like how are the bands selected to say the tip is like a hyperspectral images where you have a lot of red bands and like several red bands. Is there just some preset wavelength under the hood that they choose the band closest to, or?
It's made to be automatic in Landsat, which I use more, and the Sentinel. But you also can give the functions that calculate them, you also can give them manually the bands. So if you cannot recognize it by the description, which one, because, for example, if you have several near infrareds, there are indices that do not use the red edge, they have the next ones, so that is not automatic. You give it the band number and tell it to compute, but you say which are the bands that have to be used to compute that. So it's automatic up to one point, with the simplest case, and the other ones you have to know yourself what are the bands that you want to use, because you can extract the bands by name and you can do the calculation separately. You would just extract the bands and make your calculations in pure Julia.
Okay.
Because it's an abstract array, you do like it was numbered, so it should work. That's the idea. So when the defaults do not work, you tell it manually. The arguments, there are options made for when they need human intervention.
Okay. And that would also enable to use the true color function to display some let's say infrared bands or something like that, or make different mappings of the bands to the colors easily.
You get not sure that I understood, because what you get is the image. Okay.
Yeah.
If it is an image, you already have the colors. That's the point. But if it is something you calculate, you get a grid. And with the grid, you can put any color scale that you want.
Yeah.
I don't know if I'm answering your question or something else. Maybe Maybe not.
Maybe not completely, but I think I understand it.
Not completely understood. I would dare to say that yes, you can.
Okay.
But we have to see details. So this is the NDVI. If you just clip it for the above 0.4, you get the vegetation. This is not the vegetation. It's locations where you have the vegetation. Yeah. You can turn it into a mask, say just different from 0 or equal to 0, and you get a mask with zeros and ones where you have information and not. You can apply it to the true color image. There is one step in here that should not be necessary anymore with 6.5 GMT, which is the transparency, but when I tried it, you still need it, so I did. What that step is to save the file on disk and read it again, because it should be a transparent image that we are seeing. So apply alpha layer to the image. You have the RGB plus the alpha layer, so it should be a transparent image when you load it, for example, in another software. And this is good for what? Well, just to verifying that the NDVI worked well. Only thing that we got was green part of it. If we got any blue or red or something, it would mean that the method would have not worked well. In fact, this is with the raw numbers, with the radiance on top of the atmosphere, the results would be a bit better. I know, for example, this, I don't know if you see the mouse, this area in here is a park inside Lisbon, it's very green. You could have had a bit more of things, targets found, but I'm about to finish. What comes? Yeah, there was our paper of MATLAB, the thing that was in the root of the Julia wrapper, in the paper that we published. There was a long, I don't know, half a page of commands where you drape. Oh, did I jump anything? No? Maybe, no, I did not. Sorry, this is great. This remote S package also can read level 2 mode is data, which for those of you that know, come with the coordinates of the sensor, which means they have an array of numbers, and they have an array of longitudes, another array of latitudes, and the data is not equally spaced. Because at that reference system, the sensor, when it looks at the Navi, sees the highest resolution footstep, which is about 900 meters, but when it looks sideways, the outer beams see something like 4 kilometers. It's by design, because the Earth is a sphere, it's not a flat, it cannot acquire the regular space. It acquires the grid cell increases more sideways in the area. So that's how they furnish the data, but that's the highest resolution that they can get. It's a level 2. Well, there's also level 1, but it's still not. So it is for engineers to process and get the data. So this model can read these and automatically fetch the longitude, the latitude, the numbers, does an interpolation, which for level 2 you will use. Well, we did it 2 kilometers, because it's midway between 1 kilometer and 4 kilometers. So it automatically read the level 2, now NetCDF, before it was HDF, and then NASA decided to change all of that. It wrote a lot of things, you know, it wrote them, they're all written all the time, because they decided, listen to me, Francisco, they decided to go from HDF to NetCDF. So they brought all things. But they have it there, you can read both, and you interpolate, because the interpolation is just near neighbor, because the points are close. You could use another more slower method, it would not make a big difference. You have the data comes with quality, level 2 data, again, for those of you who know, most of the times have gaps because of the clouds. You have to try to find one with 50% data is already very good. So you have those averages, you need to have many of them. And this one, which took a long list of commands to produce, is a figure made with SST on the, of course, and on the ocean, and on land you put the topography. The operations that need to be done to this is you have to take one of the grids, take a mask of the land mass, click the image from one, and do the opposite from the land side, and then you plot one on top of the other using the transparency. Well, in pure GMT, you still have to do it. In GMT GL, I made a wrapper that's called Sealand. There is also another one called Terramar, and where you give it the parameters for the seaside, seas, GRD, the earth. Well, maybe that we cannot read. So I download the topography and put it on land, and I use the grid that was calculated from the L2 MODIS data, put them together with this single command, and then the other two commands is to add the color bars, one from the temperature and the other one from the altitude. I also applied shading, which is an operation that is more for DEMs, but sometimes it also works nicely for temperatures or other things, and that's how we see all these details, the curls in the Alboran Sea and the south. By the way, I live there. And chlorophyll also makes very nice pictures sometimes. You can do the same thing with the chlorophyll concentration. And chlorophyll concentration, because it spans for several order of magnitudes, you have to apply logarithmic color scales, otherwise you don't see nothing. But you also can make very pretty pictures like this. And see, to do this picture, well, adding more, some flowers, which is the rose, I forgot the name in English now, the Rosa dos Ventos, and things like that. Well, about finished. This is one layer. Oh, no, this is the last one. Still comes from the time of the other one with Meron. I have a collection of 20 or 21 years of downloading the level 2 data for this region, calculating the weekly averages, monthly averages, yearly averages. Yes. I started with one and that did not care. There's too much noise, more noise than they say in the data. So I had it in 1 kilometer. It was too big for nothing. So I filter, I do 2 kilometers. The file it's there in the Google Drive. It has 19 years of that. So it's a cube of SST. I just showing one of the slices. A cube slice, I sliced the third layer of the cube. And again, like the others, I made the picture. And because I have this cube, I can also do things like, let's see how it behaves on the vertical. So it means along the time. When I made these, I did not add information about the time on the vertical. So that's what one of those lines here does. What is it? Yeah, this line here is, say, collect 2001 to 2019 is to have the years instead of having just the layer numbers. So we can have a nice plots. Normally, that's one thing that should have been done when the cube was created, but was not, so I added later. Because the grid type also accounts for the third dimension, and you can give it names, descriptions. Many times you have metadata that you can also put as metadata of that type. And the next 2 and final figures is, let's see what has been happening on temperature at one point, more or less around here in the Mediterranean, and another one here. Short, please. So what I do, to take the cube and you look at the same cell along the 19 years, and you do the plot and do a linear fit to see what's the variation. And the first one is the point in the Mediterranean, where this is yearly averages temperatures. This is, okay, now he comes back. Unfortunately, a bit too big, but this, you can see the numbers. The numbers are, again, it disappeared. Okay. Yeah. So the temperature on that point of the Mediterranean, the sea surface temperature on that point in the Mediterranean has been clearly increasing. But again, contrary to the people think, that does not happen everywhere. There are places where it increases. There are many places where the signal statistical is not really nor yes nor no, and some other places is decreasing. So this is an example where it's really decreasing. You see the parameters of the fit. It's 0.48 the slope of that straight line. So it means it's 0.48 degrees per year. Not much, but if you multiply by 20 years, you already get 0.9 degrees. So that point in the Mediterranean, on average, have increased 0.9 degrees.
This is
Annual means. Well, they are more clever ways I started. They do the seasoning, to do these things. I started, I have working, and it's still on the list to be done to do it better. But only the simple operations of calculating yearly averages remove us the seasonal signal, and the results are not ready. If you do it with month, the result is much higher, many times. It's much wronger. It's a mistake that I keep seeing, I mean, even in papers. You should not do this when you have the seasonal signal on top of that, because having 1 point more or less on the two tips is sufficient to change slightly the value. So this is in the Mediterranean, but if you look on the upwelling area of the coast, the signal is contrary. Probably you know why. It's the wind, because it's been enforcing. The thing is, the temperature close offshore, the west coast, has in fact been decreasing with the time. Most of the places increases, or the signal is not convincing one way or the other. Some others are decreasing, but some, this is, and if you look at the signal with the chlorophyll, you also see a slight increase. So, yeah, there, this area? The Azores. I never look at the Azores because I use that area. I would like, but if I extend that area from what I showed you till the Azores, makes very big files, and I started to do this analysis with the MATLAB code, which is 32 bits, so I'm very limited on memory. I have to do a lot of gymnastics to be able to do this with only 32 bits, not 64. So I did not extend it to the Azores, and also because the files that I'm on were huge. But okay, I think it's my last one. This is not really very efficient because it's taking the slice entirely area when you doesn't need them. In terms of efficiency, what I should do is use what Alexander showed us with that, because it's also he showed us examples of doing similar things. So to continue this, probably the clever thing I should do is to use the work of Alexander, because he already done that type of things. I learned it 1 hour ago. Okay, and I finish here. It's not a good tool for Francisco because he wants interactive. I think it's a good tool for the quality of the figures, as I showed you in the first, but it's not what he's seeking, because he wants to click buttons and see the slices fast ways.
But we need also static.
For the static, for the interactive is not a tool for you.
We are happy also with the static.
So I think it's the lunch break now. So if you are.
Thank you very much. Okay, so for those who are online, today the workshop has already ended. For those who are in place, it's lunchtime, and Iga wants to make an announcement.
Yes, at 1:30 there is a meeting in the lobby for those of you who sign up for the tour. It starts at 1:30, and then you need to pay each of you separately for the tour. I think it will be around 40 euros. And another announcement for the speakers, those of you who didn't send a pull request, please do so, because we need to have the notebooks in our workshop repository. Yeah.
Okay.
Have a nice lunch.
Thank you.